Hello.
Hello.
Okay. Okay. So yeah. Right. Hello everyone. We are going to commence this month webinar conducted by Institute of Physics Sri Lanka. I'm Shanta Gamage, the president of Institute of Physics Sri Lanka. As you we have been organizing this webinar series to promote physics and its application, and also aware the public on 4 key topics related to science. Before introducing our resource person today, I would like to warmly welcome all the participants of this webinar. Thank you for taking time and being here today also. So, Dr. Morel Fonseca is today's resource person. First of all, let me welcome Dr. Fonseca on behalf of IPSL. We are honored by your presence. Thank you for accepting our invitation. So let me introduce briefly our resource person today, Dr. Morel Fonseca. He obtained his first degree in BSc in Physics in 1969 from the University of Colombo. Then he obtained his master degree in the field of exploration geophysics in 1973 in UK. And in 1978, he obtained his PhD from the same university in UK. He was the Marie Curie Fellowship holder in 1995 and also was the president of Geological Society of Sri Lanka in 2000. His specialization in the PhD is rock deformation in relation to the earthquakes. His major part of the career had been served as a teacher with experimental physics, exploration geophysics, and research toward the exploration geophysics application to subsurface mapping of thermal spring in Sri Lanka. Later, he worked as a consultant geophysicist to civil engineering. He has served several universities, including University of Colombo, University of Kelaniya, IFS Kandy, Open University of Sri Lanka, University of London, and University of Ontario, and University of Canada, University of Toronto in Canada. After serving a long period of time, he retired at the age of 75 in a few years ago. So today's he will present on application of magnetic-telluric geophysical technique in Sri Lanka. So over to Dr. Fonseca.
Thank you, Professor Gamage, for inviting me to this talk. I am very delighted to give this talk on this topic, which is my favorite research line. Though I did rock deformation for my PhD later when I came to Sri Lanka, I thought I had to do something that is more relevant to Sri Lanka. So I embarked on the geophysics of the thermal springs. This work I first started at IFS under Professor Cyril Ponnamperuma And after that, I continued the same work while I was working at Open University. I migrated to Canada in year 2000, but still I did not give up my ambitions in Sri Lanka. And in 2010, I embarked on a major project, Magneto-telluric subsurface mapping in Sri Lanka. So this work is related to thermal springs. I have to share this. Okay. I hope you can see this, my PowerPoint presentation.
Yes, we can see that.
Okay.
Yeah.
Now, the main object of this project is to map the subsurface of the thermal springs to find the hot water path and the extent of the hot water bodies or hot dry rock under the earth. I always have to talk a little bit of geology. So you see this Sri Lanka, and there are several sections here. And this line is called the Highland Vijayan boundary, which is the collision of two land masses long time ago in the Gondwana. So most of these hot springs are along this boundary, and that is where we were going to work. Now, we initially started doing various kinds of geophysical studies, like what you call the self-potential of the ground. The ground has a self-potential due to uprising thermal waters, so that was mapped. Then we did magnetic surveys, gravity surveys, and finally we did DC electric surveys. Now, in doing all this kind of work, resistivity is one of the best techniques to find the hot water bodies, because resistivity changes with water and also with hot rock. If the rocks are very hot, like 200, 300 degrees centigrade or 400, that way they start to conduct much better. So resistivity technique was employed. Now, as you can see in this chart, the resistivity of certain rocks are extremely high. And of course, if there is water, its resistivity is low. Now, when you do resistivity, I'm just talk of resistivity first before going into magnetotelluric. We employ this four-probe technique, which is very famous among physicists. You input current to the ground and you measure the potential between two electrodes here. And by doing this, you can measure the resistivity of the ground using this formula. I'm not going into the full theories. So we get the resistivity of the subsurface. Of course, the earth is not a pure substance. So what we get is called apparent resistivity. It is not the real resistivity because it's the bulk resistivity of the subsurface. So we call it apparent resistivity. There are other techniques where you use, now here we use both the electrode separation same, but here this volt potential separation is smaller. So we get the resistivity of this narrow strip, whereas we get the resistivity here on a broader strip. We do it along the ground at, as you what you call profiling. As you keep going, you keep mapping the resistivity of the apparent resistivity of the ground. When you spread the electrodes, like the current electrodes, here you see the current electrodes. When you spread the current electrodes, the current penetrate deeper and you get the or deeper apparent resistivities. So this is done along a line, and then once you get the apparent resistivity, you model it to get the true resistivity. So there are two ways of modeling. One is forward modeling. That means you think of a model and then you adjust the model until you get the experimental data. The reverse problem is to use the data and to get the model. Now this is the most, nowadays this is employed most. Now this idea is also used in magnetotellurics. Now when we did, okay, we did this work with several institutes. Now collaboration is a major part of my work. There was the Water Board, the Geological Survey and Mines Bureau, the University of Edinburgh, because University of Edinburgh, they send students to me over several years, like almost up to 7-8 years, and they bring the equipment and we did this work. Now, one thing that happened with this investigation, initial investigation, was that the top rock is highly conducting, naturally, because top surface has a lot of water, groundwater, and the deeper rocks are extremely resistive. And this our normal resistivity technique was not working very well. I used even electrode separations up to 2 kilometers. So 2-kilometer electrode separation, and in between them the potential electrodes. Even that 2-kilometer electrode separation, current was not penetrating more than maybe maximum 100 meters. So, but we could investigate was up to about 100 meters. That did not give us much information, except it showed some of the thermal water paths. So the next stage is to use low frequency electromagnetic waves. Electromagnetic waves penetrate deeper into the ground if they are of very low frequency. The very low frequencies can penetrate even up to thousands of kilometers. So that was the idea behind this next stage of work. Now, we use natural electromagnetic waves, and they are generated by interaction of the solar wind with the Earth magnetic field, and that generates electromagnetic waves. Also, lightning that happens globally, it creates electromagnetic waves, and by way of waveguide phenomena, it travels around the Earth, and they are also used. Now, in our work, we were using periods from 0.001 to periods of 10,000 seconds. So 10,000 seconds is extremely long period electromagnetic waves. Now, initially, this idea, what you call magnetotellurics, the magnetic field and the electric field is monitored to study the surface, study the subsurface. There had been some initial work done by Professor Kannangara and Professor P.C.B. Fernando. Professor Kannangara was at Colombo University, and then Professor P.C.B. Fernando was at Sri Lanka. Professor Kannangara was monitoring the magnetic field, and then Professor Fernando was monitoring the electric fields, and they did some of this work as late as mid-1960s. And I remember I was at the basement of the Sri Jayawardhanapura doing some measurements for them. At that time, they were using chart recorders and, very primitive, from the modern standard, very primitive equipment. And they could only monitor extremely long periods because chart recorders cannot do fast recording. And they were reaching somewhere the Earth's mantle. And they found very low resistivity in that part.
Dr. Ponseca, excuse me.
Yes,
Yeah, please use presentation mode so that we can see the enlarged view.
presentation mode. One second. Presentation mode.
So in the bottom right corner, there is an icon. Oh, okay, now it's okay. Now it's okay.
Okay. Is that right now? Can you hear me?
We can hear you, but your presentation is, your slide is not that clear. Please share the screen again. Anyway, please carry on. Anyway, go ahead with this.
Okay. Okay. Now with Magneto-tellurics, we monitor the electric field and the magnetic field at the ground surface, because these electric fields and magnetic fields are modified due to the subsurface, and they are monitored using, in our case, we use 2 magnetometers. We are doing 2-dimensional work, not 3D. 3D needs 3 magnetometers. So we have 1 magnetometer facing north, 1 magnetometer facing east or west. And the electric field is monitored using ground electrodes, non-polarizing ground electrodes, because you can't just put iron stakes because they polarize and give wrong voltages. So we have non-polarizing electrodes, which is copper wire put into a copper sulfate solution in a porous pot. Magnetometers have to be buried to avoid vibrations, because these are extremely sensitive magnetometers, massive ones, so they are put there and the data is digitally recorded. Now, apparent resistivity in this electromagnetic technique comes in this formula, which is 0.2 into the period electric field vector, electric field divided by the magnetic field in the x and y direction. So that gives what you call rho xy, that is the apparent resistivity as measured in the xy direction. And then using the x electric field and y electric field, then there is a similar one, which is using the y electric field and the x magnetic field. And then there is what you call the skin depth of, everybody knows the skin depth. Depending on the wavelength, it penetrates the deepest. So the skin depth is given by this formula. So finally, what we have is, depending on the period, so longer periods will be measuring deeper, more deeper layers and getting the apparent resistivity. Whereas the shorter periods will be giving more on the near surface. And this is the depth. Of course, this is the skin depth. That is roughly equal to, because the permeability of the ground is mostly the same for most of the rocks. So finally, we end up with this simple formula. So once the apparent resistivity is found and the skin depth is known, we go for modeling. So once, we have been doing the inverse transformation, not the forward modeling, but the inverse modeling. And then that gives the map, subsurface resistivity map. The model must generate the same values as the experimental values. Of course, this is a very complicated, extremely complicated process. On this picture here, you see some of the signals we have been recording at Mahapalasa, and you can see the electric field and the magnetic fields are very coherent and they are going in the same way. But in the other direction, it is slightly somewhat not all that good. And it's the same recordings I show you here. Now, as I said, I had to collaborate on this because this project is an extremely expensive one, and you can't just imagine. Collecting one set of data at one single point is $2,000 in the modern sense. Just collecting the data, not including transport, logistics, everything put together. And we did almost close to 120 data points, sampling points all over the country. So I had to sort help, and it's a long story because Professor Ponnamperuma said, he can't give funding for this kind of work. I have to look for it. So I sought all around the world and finally landed with the Edinburgh University with Professor Rosemary Hutton. Now she is, she is now past. So this is Professor Rosemary Hutton, one of the famous geophysicists in the world. She has done a lot of this kind of work in Africa, all over the world. And it was Professor Paul Barnes, who was instrumental in awarding this Marie Curie Fellowship to me, and which made me to go and meet Rosemary Hutton. And then Rosemary Hutton retired, and then Professor Bruce Hobbs came into the scene. And this is Professor Barker, who came to do some resistivity work with us some time back. And Professor Kathleen Whaler was instrumental to get the equipment loaned from the NERC, National Environmental Research Council in UK. And this is Dr. Alan Jones, one of the famous persons on modeling of MT data. Of course, Professor Bruce Hobbs used what we call multi-transient electromagnetics, and he developed a technique which is a secret, and it has been given to petroleum geoservices, which can, using similar techniques, he can tell if a petroleum well is oil, gas, or empty. So this is the kind of people who helped us in this work. And Professor Bruce Hobbs, I must tell, he put a lot of money to this program. And he was instrumental in bringing the equipment to Sri Lanka, which is almost a container load of equipment. All airfares, custom clearance, bonds, everything was placed by him. And also, Institute of Fundamental Studies, Geological Survey and Mines Bureau, they all helped us with the logistics and so many things. Dr. Vijayananda, GSMB chairman at that time, Professor C.B. Disanayaka at IFS, then Water Supply and Drainage Board, they all helped us. And it's a lot of work, it's a teamwork. Now, field operations started and we needed several parties. There's an advanced survey team who has to select the sites and get the profile, like 20, 30 kilometer long straight profiles through the jungles. So advanced party to obtain security clearance from police and all that kind of thing. Then an advanced party setting up the Magneto-telluric equipment and what you call the transient electromagnetics. This is another subsidiary work which is far better for near surface work. Then another party for data acquisition. You can see the magnetometers here being laid down, and one in the north direction, one in the east west direction. And this is the transient electromagnetics, which uses another techniques to near sample Earth. You can see the amount of people that were involved in this work. I must say Professor Subha Singh at IFS was also involved, and he helped a lot. And there was now Dr. Titus Kure from Sabaragamu University, I think. He was leading the survey party. Nalin De Silva from GSMB, he did a great work in organizing so many things, and I mean, it's immense amount of work done by him. You can see the initial party of people: Professor Bruce Hobbs, myself, Graham Dawes, he's the technician, he was instrumental to keep the equipment running properly. This is the initial, very first day of organizing everything to go on the field work. And this video shows field party going in the jungle. Now, the data was collected. It's a vast amount of data. Of course, the instrument, I am not discussing too much about the instrumentation because, I mean, there were so many, we were recording on various frequency bands, day and night, and the work went for up to nearly 2.5 months collecting data day and night. And each site was sampled at least for 24 hours of data collection. Now, these are some of the results of apparent resistivity. The blue part is done by the TEM, the transient electromagnetic, the red part done by the magnetotellurics. So we make the apparent 2D apparent resistivity maps. This is the apparent resistivity map, the very first one. And this is the phase map, the phase between EX and HY. And and the other component, we have two perpendicular components. Now, these are some of the maps we made, underground maps, subsurface maps. And this is at Mahapalasa. And here we identify this one as the Highland-Vijayana boundary between the, the collision of the two land masses in very long time ago in the Gondwana. And the hot spring is here. Of course, in this one, we don't see much a large location of hot water, except at the very near surface. This is the Kenya Moravava Traverse, Kenya in Trincomalee, and you can see hot water accumulation at depth. We expect this is hot water because there is very low resistivity here. And also these models has to go in line with the surface geology maps, so that, because sometimes you don't know whether the model is the correct model. So it has to be identified with the other geologic maps, boreholes data to get the exact model. This is the Mahawe area. Here you can see the Mahawe hot spring is here. Mahawe hot spring is about 55 degrees centigrade. And you can see at a depth of about 10 kilometers, there is a very low resistivity zone. And this one goes towards the Padiyatalawa hot spring. Of course, now this is the Padiyatalawa hot spring. And you can see there are connections, the low resistivity connections towards the deeper interior. And in the Padiyatalawa one, at a depth of something like between 10 to 20 kilometers, there is a very low resistivity zone. So now we don't know what this is, whether it is hot water or it is hot rock. This is Kapural hot spring. I think it's, this one, Kapural is the highest temperature hot spring, which is 65 degrees centigrade. And it also shows some connection to the deep interior. There is an accumulation of quite a lot of hot water somewhere down here. This is another one at Padiyatalawa, which had the very hot zone about 20 kilometers down. It's somewhere, this is the top 2 kilometers. So this is in a nutshell, what we did and what we have achieved. And the important thing that relates to this work is that with collaboration, you can do a lot of work. Of course, funding is a big problem especially for the Sri Lankan scientific community. So if you have the right project, there are people out in the world who are ready to help. And so if you are persevering, it can be achieved. So thank you for listening to my talk. I have made it very brief because of the time that is given to us. I hope you enjoyed my talk, and thank you again for listening to my talk. Thank you.
Thank you very much, Dr. Ponseca, for very interesting presentation. Now the topic is open for the discussion. You can ask questions if you have related to this topic. Well, actually, I was also the participant of the workshop that conducted by yourself with Dr. Bruce Hobson, Ian Barker in I think 1990. I forget the 1997 or 1998 period. I also
I'm glad to
participated.
hear.
I also participated that workshop, which was held at the. I think the second day was at the Atomic Energy Institute or somewhere else. I forget the place. Anyway, I participated. Those one of the workshop that conducted by Dr. Bruce and Barker, and also with yourself when you were in Open University in Sri Lanka.
Yeah.
And regarding hot spring, uh, what is your idea about hot spring? What would be the reason? Of course, it's very clear. We have idea about the reason for the occurrence of having hot spring in other part of the world. But in Sri Lankan situation, how do you explain the existence of hot spring?
Well, I think there is one paper by Dharmasiri and Basnayaka long ago, from CISR. I think they did that work maybe in the late 1950s. They studied the tritium content, and that indicated the water is meteoritic, which means it's the rainwater that has been percolating deep into the ground through the fractures, and they are uprising again. They enter from the mountain, fractures, and they go deep down. The gravity model in Sri Lanka shows deep block faulting on the ground, and so it must be going deep into the ground and coming up. So when you go deeper into the ground, the earth, the temperature gradient is about 18 to 22 degrees centigrade per kilometer. In Sri Lanka, in Puttalam, they say it's about 22 degrees centigrade per kilometer through borehole measurements by the Russians for petroleum. So when you go deep into the ground, they get warm and then come out. So that's the most likely explanation. Of course, there are other things. The last magmatic event in Sri Lanka was about 450 million years ago. I think it's 450 or 150, I can't remember. I mean, if those deeper hot bodies, those magmatic bodies, if they are still hot through radioactive material that decay through them, that may also be generating heat. That Padyatalava case where we saw about 10 to 20 kilometers down below, there's a very low resistivity zone, which may be a hot body, and in that region, there are what you call dolerite dikes. Dolerite dikes are deep intrusions from the earth, deep magmatic intrusion from the earth. So it could be a possibility. I mean, these are all possibilities. I mean, if one day the world will be developed enough to do cheap drilling, because at the moment drilling is quite expensive, and if we drill deep into the earth, we can extract the heat. So if there is a hot body, we can use it. We have to wait for some time for these technologies to get better. I mean, drilling for petroleum is cheaper because cheaper in the sense they are drilling mostly sedimentary rocks, which are more not so hard compared to our Sri Lankan rocks, which are what we call the metamorphic rocks, extremely hard rock.
Yeah, I think you're talking about geothermal power plant or something, but the problem is the temperature in the case of Sri Lankan situation. Anyway, in regarding the Kapural hot spring, is actually it's the hottest one in Sri Lanka, as you mentioned, and the reason is the accumulation of deep interior of the accumulation is the reason.
That's the most likely reason that the water enters from the highlands. Water enters from the highland and then go deep down through the fractures. Then by Artesian action, it's coming out on the lowland areas. So they go deep into the earth and then get heated and then come out. Of course, on the way they cool down, but still, of course, thermal conductivity of rocks are very low. So they managed to come out and still show some temperature, some elevated temperature. That's the most likely explanation at the moment.
Any more questions? If you have a question, if you cannot ask, you can type and send as a chat also. Send to the chat box also. Please don't hesitate to ask question if you have any. Regarding the relationship between hot spring and earthquakes, what is the relationship? Because recently we have experienced in several earth tremors in eastern part of Sri Lanka near hot spring. Do you have any idea about the reason for the occurrence of that type of earthquakes near hot spring?
The eastern part.
Yes, of course, in 2012, several tremors took place near hot spring. There's any possibility of occurring these earthquakes for the? Of course, there are several explanations, but I want to know your idea about that.
I mean, what I can think is
of course, their explanation was actually 2012. There was a big earthquake occurred in the region of Sumatra. That is strike slip earthquake. Therefore, the energy accumulated due to that earthquake it could be the reason for the occurrence is one explanation. But I just asked you your
energy stresses. So it's releasing the stress. They get compressed because of the plate movements. They get stressed. Now I know down south of Sri Lanka there is a new plate margin being developed. It has been monitored. The Earth's ground surface in the sea is getting. You see something like if you compress a cloth, it bends into like nappies. So something like this happening, which indicate compression, and this very likely that there is a new earthquake belt being built up in southern Sri Lanka. So compressions happen. It's very difficult to give a real answer to this kind of things unless somebody investigate these things in detail through seismic work. So compression is one thing. So plates compress in different ways. We don't know where they are compressing. So such compression can give fractures. Or existing faults can slip. Now, I don't know whether this could have happened there. Now, we know when you impound a dam, when you make a dam and fill up the reservoir, the water penetrates into the fractures and then slips occur. So, I mean, in the long term, whether anything like that happened, because compressions are going on, and if the fractures get lubricated, it can slip. That do happen. So that can be a likely explanation. Of course, the energy of some other earthquake. When you say energy, means it's the compression, energy in compression. So the plate got compressed, and somewhere where there had been a weak point, or where there is already existing fractures, that compression can give the slip and create earthquakes.
Okay, thank you very much. Any more questions? Any other questions? Comments? If no more question, I would like to thank today's speaker, Dr. Morel Fonseca, for accepting our invitation and giving excellent presentation. Thank you very much for it. We were able to learn a lot of new things from you. You were the one of the famous geophysicists in Sri Lanka in those days. And also I take this opportunity to thank all the participants for this webinar series. Thank you for making the time to watch our seminar today also. We hope that you will be with us, our future activities too. Hope to see you in next webinar too. Thank you very much. Thanks all.
Thank you, Professor Gamage. Thanks. I'm very glad that you invited me to this talk. It was a pleasure for me to give this talk, which on the work that I did so much with dedication. Thank you again, and thank you all the collaborators who may not be present. Professor Bruce Sobb said he will try to join, but he has been under surgery, and so maybe he could not join. So thanking all the collaborators also at this time. Thank you very much.
Okay, thank you very much, sir, for your kind accept. Thank you all.
Thank you.